One day without warning, the sun will change, not explode, not disappear, but quietly grow until Earth itself can no longer survive. This is not science fiction. This is the future. These words settle in the mind with the weight of cosmic truth, a quiet and profound statement about our place in the universe. They are not meant to inspire fear, but rather a deep and sober contemplation of time that dwarfs human history. They invite us to look up at the familiar star that warms our skin and nourishes our world, and to see it not just as a constant presence, but as a dynamic entity with a life story all its own. A story in which we are but a brief, beautiful chapter. We begin. Long before there was an Earth, long before there was a sun, there was only a vast, cold, dark expanse of space. Drifting within this void was an immense cloud of molecular gas interstellar dust, a nebula spanning light years across. For millions of years, this cloud existed in a delicate equilibrium. Its faint gravity gently pulled inward, while slight pressure from sparse atoms pushed outward. But the universe is not a static place. Then a disturbance, perhaps a shockwave from a nearby supernova, rippled through the nebula. That cosmic nudge upset the balance and triggered irreversible collapse. Gravity, the silent architect, took command. The cloud began to contract, funneling material toward dense regions. Gas dust fell inward, and the cloud fragmented into smaller, spinning clumps. At the heart of the largest clump, our solar nebula, material concentrated. Pressure temperature began to skyrocket. The center glowed with a dull red heat. A dense, hot, spinning core, a protostar, formed. Not yet a true star, but racing toward ignition. Celestial chaos reigned. The nascent sun ravenously accreted material from the surrounding disk of gas and dust. The accretion disk, a flattened, swirling carousel of matter, fed the protostar, heating and brightening it. For millions of years this continued. The core became a crucible of immense pressure and extreme heat, millions of degrees. At a critical threshold, pressure and heat forced hydrogen nuclei to fuse into helium. Nuclear fusion unleashed vast energy, producing outward pressure to counter gravity. A star was born. The sun settled into main sequence equilibrium. Powerful stellar winds blew away remaining gas and dust, unveiling the young star. And that is how it began. As the young sun ignited and began its long, stable life, the surrounding accretion disk was a chaotic construction zone. The material that was not consumed by the star or blown away by its solar wind began to coalesce. Microscopic grains of dust, coated in ice, stuck together through electrostatic forces, forming larger and larger clumps. These clumps grew into pebbles, the pebbles into rocks, and the rocks into kilometer-sized planetesimals. Through countless collisions over millions of years, these planetesimals continued to merge and grow, their own gravity sweeping up smaller debris in a process known as accretion. This was the violent and messy birth of the planets. In the inner regions of the solar system, closer to the sun's heat, only rocky materials could condense. Metallic materials could condense. This gave rise to the terrestrial planets: Mercury, Venus, Earth, Mars. The early Earth was a hellish world, a molten ball of rock constantly bombarded by asteroids and comets left over from the solar system's formation. This period, known as the Late Heavy Bombardment, was a time of immense violence. One cataclysmic collision with a Mars-sized object named Theia is thought to have blasted a huge chunk of Earth's mantle into orbit, material that eventually coalesced to form our moon. Over time, the bombardment subsided and the planet began to cool. A solid crust formed over the molten interior. Volcanic activity was rampant, releasing water vapor, carbon dioxide, and nitrogen from the planet's interior. This process, called outgassing, created Earth's first primitive atmosphere. As the planet continued to cool, the water vapor in the atmosphere condensed and fell as rain for millennia, filling the vast, barren basins of the crust. These torrential downpours formed the first oceans, creating a warm, shallow, chemical-rich environment, a primordial soup that held the potential for something extraordinary. It was in this specific environment that life found its foothold. Earth was in the Goldilocks zone. That's where we started. With the solar system settled into a more orderly state and Earth cooled into a water world, the stage was set for life's grand epic. The Sun entered the longest and most stable phase of its existence, the main sequence. For billions of years, it has been steadily fusing hydrogen into helium in its core, releasing a consistent and reliable stream of energy. This stellar stability has been the single most important factor in allowing life on Earth to not only emerge, but to evolve and flourish in breathtaking complexity. The Sun's calm, predictable output provided a constant source of warmth and light, creating a stable climate over geological timescales. During this long, quiet era, life began its slow but persistent transformation of the planet. The first simple, single-celled organisms evolved in the primordial oceans. Through the revolutionary process of photosynthesis, some of these early microbes, like cyanobacteria, began to harness sunlight directly. They used its energy to convert carbon dioxide and water into food, releasing oxygen as a waste product. Over hundreds of millions of years, this waste fundamentally altered Earth's atmosphere, leading to the Great Oxidation Event. This dramatic change was toxic to much of the early anaerobic life, but it paved the way for new, more complex life forms that could use oxygen for respiration. The Sun's unwavering light fueled this biological revolution. With an oxygen-rich atmosphere and the formation of an ozone layer to shield the surface from harmful ultraviolet radiation, life was able to move from the protection of the oceans onto the land. Plants covered the continents, creating vast forests and grasslands. Animals followed, diversifying into an incredible array of forms. This long period of stability, this long midday of the Sun's life, allowed for the slow, patient process of evolution by natural selection to work its magic. It gave time for ecosystems to develop, for species to adapt, and for intelligence to eventually emerge. We as a species are a product of this remarkable stability. Human civilization arose in a geological blink of an eye, entirely within this period of stellar calm. We learned to chart the seasons by the sun's path, to grow our food with its light, and to mark our days by its rising and setting. Well, that's the long, stable midday we've known. Like all things in the universe, the sun is not immortal. It is a middle-aged star, roughly 4.6 billion years old. It's about halfway through its main sequence lifetime. The nuclear fusion in its core, the engine that has powered it, is a finite process. Every second the sun converts about 600 million tons of hydrogen into helium. The sun's fuel tank is vast, but not bottomless. As it burns hydrogen, the core's composition slowly changes. The proportion of helium ash steadily increases. The amount of hydrogen fuel dwindles. This gradual change starts the sun's aging over hundreds of millions of years. As hydrogen concentration falls, fusion reactions slow down. Gravity begins to win against fusion pressure. The core starts to contract. The core heats up. The hotter core makes the outer layers burn hydrogen more furiously. The sun becomes more luminous. It gets brighter. It gets hotter, outputting more energy into the solar system. This slow brightening is the first sign of the sun's impending transition. Over the next billion years, luminosity rises by about 10%. For Earth, consequences are profound. Increased solar energy triggers a runaway moist greenhouse. Higher temps cause more ocean water to evaporate. More water vapor accumulates in the atmosphere. Water vapor traps more heat. That causes more evaporation. A devastating feedback loop slowly boils the oceans away. Eventually, after several billion years, hydrogen in the core is exhausted. Fusion in the core ceases. The star transforms dramatically. The inert helium core contracts and heats immensely. hydrogen fusion ignites in a shell around the helium core. That shell burning pushes the outer layers outward with tremendous force. The sun begins to swell. Its surface cools. Its surface reddens. It transforms into a red giant, the start of its final dramatic phase. As the sun embarks on its journey to become a red giant, the Earth will face a series of catastrophic changes that will render it utterly unrecognizable. Long before the sun's physical expansion reaches our planet, the escalating heat will seal its fate. The runaway greenhouse effect, initiated by the sun's increasing luminosity, will have boiled the oceans dry. The once blue planet will become a vast, desiccated desert under a relentlessly brightening sky. The water vapor that once filled the atmosphere will be broken down by intense solar radiation into hydrogen and oxygen. The light hydrogen gas will escape into space, ensuring the water is lost forever. The heat will become, unimaginable. Surface temperatures will climb to hundreds of degrees Celsius, high enough to melt lead. The very rocks of the continents will begin to soften and bake. Earth's atmosphere, stripped of its water and battered by an increasingly powerful solar wind, will be gradually eroded and blasted into space. Without an atmosphere to protect it, the surface will be exposed to the full, raw fury of the sun's radiation. Any last vestiges of life which might have clung on in subterranean pockets or near polar ice caps will be extinguished. The planet will be sterilized, its long and vibrant biological history erased by the fire of its own star. The sun will continue to swell, growing larger and larger over millions of years. It will engulf Mercury first. It will engulf Venus next. Its outer edge will loom terrifyingly large in Earth's sky, a vast, incandescent wall of red-hot plasma. Some models suggest that as the sun expands, it also loses mass through a powerful stellar wind, weakening its gravitational pull. That could allow Earth's orbit to migrate slowly outward, perhaps just enough to escape being swallowed. Even if it escapes direct engulfment, Earth would be a charred, molten cinder orbiting the sun's outer atmosphere. Tidal forces would lock Earth's rotation, one side facing the inferno, the other frozen in shadow. The surface would be a sea of magma. Eventually, drag from the sun's chromosphere would cause Earth's orbit to decay. In its final moments, our planet would spiral inward. The Earth as a physical object would cease to exist. The forecast of Earth's end is a distant but certain one, presenting a profound, long-term challenge to the future of life originating from this planet. The timescale, spanning hundreds of millions to billions of years, gives us an immense runway. It is not a problem for tomorrow or the next century, but it is an ultimate existential question. If intelligent life, whether human or post-human, is to survive, it cannot remain on Earth indefinitely. We are living in a temporary cradle, and one day we will have to leave. The choices we face fall into several broad categories, each with its own monumental set of challenges and possibilities. The first and perhaps most conservative option is to attempt to stay within the solar system, but to move. As the sun's habitable zone slowly shifts outward, so too could we. Mars, currently cold and arid, would warm. With significant terraforming efforts, it might become a temporary haven for a few 100 million years. Further out, moons of Jupiter and Saturn would begin to thaw. Europa Titan. Their subsurface oceans could become vast, global liquid water habitats, new cradles for life. This strategy is planetary migration, a slow retreat, hopping from one world to the next. A more ambitious approach would be to abandon planets altogether. We could construct massive, self-sustaining artificial habitats. O'Neill cylinders. These worldlets could orbit the sun at any distance we choose. They could replicate Earth's environment internally, with ecosystems, atmospheres, and gravity simulated through rotation. Such structures would allow a civilization to harness the sun's immense energy output even as it grows into a red giant. This path represents a transition to a truly spacefaring species, masters of engineered environments. These options, however, only delay the inevitable. The sun itself will eventually die, shedding its outer layers, collapsing into a white dwarf. The ultimate solution for long-term survival is to leave the solar system entirely. This is the challenge of interstellar travel. It would require building arc ships capable of sustaining generations of travelers. We would need to identify nearby star systems with potentially habitable planets or build vessels capable of creating their own habitats upon arrival. This is the most technologically daunting path, demanding propulsion systems beyond our current imagination and solutions for the biological and psychological challenges of multi-generational voyages in deep space. The universe does not rush, it waits. And one day, the sun will remind us, nothing lasts forever. The prospect of interstellar travel represents the ultimate graduation for a species born on a single planet. It is the final and most profound answer to the sun's inevitable aging. Leaving our solar system would not be an act of abandonment, but an act of preservation, carrying the legacy of earthly life outward into the galaxy. The challenges are almost incomprehensible from our current vantage point. The distances are the primary barrier. Proxima Centauri is over 4 light-years away. With our fastest current technology, a journey would take tens of thousands of years, far longer than recorded human history. We would need revolutionary breakthroughs in physics and engineering, fusion rockets, harnessing the energy of the vacuum, enormous light sails pushed by powerful lasers. These ideas live in theory and science fiction, but they are not forbidden by physics. The sun's slow advance gives future generations time to turn theory into reality, to build ships to new suns. The journey is as much biological and societal as it is technological. A worldship must be a perfectly closed ecosystem, recycling every atom of air, recycling water, recycling nutrients for centuries or millennia. It must be a stable society, able to weather generations of confinement without collapse. Travelers arriving will be separated from their ancestors by an unimaginable gulf of time. They will be carriers of memory, biological seeds, cultural seeds from a world that may no longer exist as they knew it. This grand exodus would fulfill our exploratory impulse. From ancestors leaving Africa to populate the continents, to the first steps on the moon, humanity is defined by the drive to see what lies over the next horizon. A journey to another star would be the final expression of that spirit. It would testify to life's tenacity, its ability to adapt, to plan, and to reach for survival against cosmic deadlines. Leaving the cradle is not just escaping an end, it is seeking a new beginning. Thinking about the end of the earth can feel heavy, casting a long shadow over our present. It can make our daily struggles and grandest achievements seem small and fleeting. Yet, adopting this cosmic perspective can also be profoundly liberating and meaningful. It reframes our existence, not as a permanent fixture, but as a precious and temporary opportunity. The knowledge that our world has a lifespan, defined by the life of our star, imbues our time here with a deeper significance. It highlights the incredible improbability of our existence, the sun's stability, Earth's protective magnetic field. This long view teaches us that change is the most fundamental law of the universe. Nothing is static. Stars are born from clouds of dust and gas. They live for billions of years. Then they die, enriching the cosmos with heavier elements forged in their cores. These elements then become the building blocks for new stars, new planets potentially, new life. The end of our world is not a final, absolute end. It is part of an immense, ongoing cycle of creation and destruction. The very atoms that make up our bodies, our oceans, and our planet were once part of long-dead stars, and they will one day be recycled into new cosmic structures. This cyclical nature of the cosmos offers a strange but powerful form of continuity. While our planet will be gone, its matter will not be destroyed. It will be returned to the interstellar medium, a contribution to the future. Our sun's final act, as it sheds its outer layers to form a beautiful planetary nebula, will seed the surrounding space with the elements necessary for future generations of stars and worlds. In this way, the story continues. Life, as a phenomenon, may end here, but its fundamental ingredients will be scattered, ready for the next cosmic chapter. It is a humbling thought, connecting our finite existence to an infinite universal story. And so, we are left with a quiet and powerful truth. The sun, which gave birth to our world and nurtured life into existence, will also be the agent of its end. This is not a tragedy. It is the natural, elegant, and inevitable rhythm of the cosmos. It does not demand fear, but rather a deep and abiding respect for the vast scales of time and the intricate dance of matter and energy that governs everything. It calls on us to be wise stewards of our world while we have it, and to dream boldly of the futures we might build. The universe does not rush, it waits, and one day the sun will remind us, nothing lasts forever.